Okay, okay. Thank you. Thanks for the introduction. And sorry for not being able to be there. So for those who do not know me, my name is Hu-aike. I'm currently a assistant professor at the International Center for Theoretical Physics, Asia Pacific. And this institute is affiliated with the University of China Academy of Sciences. So I hope so. You're all welcome to come and visit us. So the talk today is about the
Hu-aike, is it possible to speak a little bit louder, please?
oh, is there some problem?
Yeah, yes, now it's better. Yeah.
Okay, okay, sorry. Uh, so the topic is about the cosmic phase transitions, and I will focus a little bit more on the one particular source, the sound waves, during this process, and how we can determine the spectrum from this source, and how can we actually detect this source. Okay, so this talk is about the cosmic phase transition that can happen in the early universe. So it's a first order phase transition, and just like a boiling water. And as this process goes on, it will turn into a different kind of picture. So this is actually what we call sound waves in this process. So the bubbles eventually will disappear, but they might be still sound waves, and this describes the kind of energy distribution across the space. And if the Reynolds number is large, then it can develop into another kind of phenomenon, turbulence. So, and it's called magnetohydrodynamic turbulence in this context. So this cosmic phase transition is quite very important, not only for cosmology but also for particle physics. And I think probably Rusuk Gino has talked about this, and probably Thomas Constantine will give you lectures on this, and Graham White and probably Mary, we all touch on this kind of topic. So the cosmic phase transition for the most important type of one is the electric phase transition, and it connected with the electric symmetry breaking. And we believe that it should be a first order so that we can generate the background symmetry that we observe in the universe. And because of a new to gravitational waves, this field has become very active, and it has connection with Higgs physics and searching for CP violation with high precision measurements, and also of course other collider observables. And you can go to Michael and David Morris's review paper for more details. So in this field, usually the research divided into this kind of several steps. So we started with some particle phase model, probably with new particles or other new things, and we calculate a bunch of phase transition parameters, alpha, the energy released from phase transition, normalized by some quantity to make it dimensionless. And beta is like some kind of frequency or inverse time scale. And VW is wall velocity in the previous paper. A figure about the bubble, how the bubble expands and how fast it expands. T star is the temperature when the phase transition happens, and GS is the relative degrees of freedom for entropy. And once we have this set of observables, we can go and calculate or from large-scale simulations to obtain a set of spectrum. So this kind of spectrum is for stochastic gravitational wave background, different from the gravitational wave signal from the binary system. Of course, they are the same kind of gravitational radiation predicted by general relativity, but it's on the experimental side, they behave differently. It's like a noise, and it's described by this omega GW, the energy density spectrum. And the blue one is just one example for phase transition. So once we have this spectrum, we can go and do a detector simulation and see how the data look like. So this is how theorists think about this problem. And as the experimentalist, so once we have the data, we can go and check if there is a stochastic background of this shape. And then we try to infer the parameters for the phase transition parameters and try to see which particle physics model is responsible for generating these phase transition parameters. And of all this kind of so gravitational wave is thus a new observer, and it can be used to view the information about the underlying particle physics. And one of this is which is very important is the so-called collider and gravitational wave complementarity. And people have studied a lot about this kind of this possibility of, for example, this is for the simplest extension of the standard model with a single addition to the model. And so the plot is about the deviations from the standard model predictions about the Higgs cubic and quartic couplings. And all these points can give strong detectable gravitational waves in space. And you can see, so I haven't imprinted the bars. They denote the set of the precision of the measurement for the cubic coupling. And it's very difficult, of course, to measure this coupling. And these are taken from another paper. So they are overlaid on our plot. So from this, you can see that even for small deviations of the couplings, we can still have this strong detectable gravitational waves. So in this region, we probably can use gravitational waves to see more about the measurement of these very important couplings. And so this is just one simple example of this complementarity. This is work done with Tathagata and other collaborators several years ago. Of course, similar studies exist in literature. For example, Andrew, they have done this a long time ago. So speaking about the sources for the gravitational production, according to the current understanding, we have mainly three contributions. So this is the Einstein equation, and this is the energy momentum tensor that can generate the gravitational waves. So one scenario is that by assuming that the energy is concentrated near the unclouded walls, and this is the approximation that people have considered in the 1990s by Arthur Kossowski and Marko Kominkowski and others. So assuming this kind of energy concentration, you can go and calculate the spectrum by, for example, following Steven Weinberg's Gravitation and Cosmology book. Later on, people realized that so this is given by the Helsinki group, that the sound waves in the process should give a dominant contribution to the gravitational wave production. So where does this sound waves come from? So as the bubble expands, so actually the bubble corresponds to some kind of scalar field, like the Higgs. As we interact with the particle in the plasma is made of relativity particles, and they're in equilibrium, more or less. And so because of the interaction, the energy can be injected from the kinetic energy of the bubble wall into the plasma. So the fluid or the plasma will be perturbed. So the perturbation in the plasma is called sound wave. So it's similar to the sound in the air. So as I'm talking, there will be sound in the rooms, and it's similar, just the medium is changed to a plasma with made of relativity particles. So yeah, so this is one source, and possibly the dominant source for gravitational wave production, at least for the electric wave transition. So if the Reynolds number of the system is large, it can turn into magnetohydrodynamic turbulence. So right now we have more or less a set of spectra for each of these sources, and so here, omega is the energy density spectrum normalized by the critical energy density of the universe. And of course, because it's a wave, it's the energy distributed into the frequency bin in a logarithmic kind of scale. And one for bubble collision, for sound waves, and for magnetohydrodynamic turbulence. I think people have used this a lot in the past. These are taken from Chiara Caprini and others, a review paper back in 2015. So of course, there's a new addition, the so-called Opson factor, and it's a factor that we discovered together with Graham White. and other collaborators like Koushik in Oklahoma and the student Daniel Vigge. So this describes the effect the following effect. So the universe expands, and in this universe there are sound waves, and so imagine we are in this room and sound are propagating in the room, right? So they can generate gravitational waves. And the walls are if we let the whole room to expand and the walls goes back, and you will notice that the energy density of the sound of the air, or in this context, the plasma will be reduced. So then there will be little kind of production for this environment. So this open factor describes this kind of effect, and it approaches 1. So the gravitational wave production will saturate to a fixed value 1. So this is what people used in the past. And the input parameter to this function is the lifetime of the sound. So if the lifetime is not infinity, then you will have a value that's less than 1. Recently, we have generalized this into a kind of more general cosmological context. I will talk this a bit more later. So even without doing a very strict calculation, we can understand the basic properties of this for the spectrum. So it has a broken parallel form, and at a very low frequency, it's F cubic due to causality. And at high frequency, it drops. So there's a peak. The peak and the slope, they are very important for detection. So the position of the peak is more or less given by this formula. Basically, it says that the scale that generates the gravitational waves is given by a particular scale, which is 1 in 100 or 1,000 of the horizon size. And if we have this scale, we can redshift this because gravitational wave just redshifts after its production. We can get a relation between the temperature when this happened and the current peak frequency, and then we can translate this into the then can translate this into the detector that we can use to detect a particular frequency of gravitational waves. For example, for LIGO, we can detect PeV to EeV scale phase transition. This is 10 to the 3 to 10 to the 6 TeV. And it's very high scale. And for the electric phase transition, so you will see that its frequency falls right within the detector in space, like Lisa and Tianqi. And for non-Hertz gravitational wave, you will see that it can correspond to the QCD scale, not necessarily the QCD phase transition. Therefore, this has become a target for the 3 major kind of detectors, and people have studied a lot of this. At LIGO, we are also trying to detect this kind of stochastic background wave. I believe Mary, my collaborator, will talk more probably on the detection. So the stochastic background gravitational wave is just like a noise in the detector, and there's a special technique to detect it. Because it's noise, we cannot distinguish it from the other noises in detectors. So we cross-correlate the data streams from 2 detectors to fill out the noise, but keeps only the signal. This is called a cross-correlation technique, because the signal can affect the 2 detectors simultaneously, while most noise will just affect only 1 detector. So and we have done so using LIGO's 01 to 03 data. And so far, we found no positive detection in our data, and we have thus placed limits on the different kind of scenarios, like the generic broken parallel model, or a model where our collision makes the dominant contribution, and another one where some waves is the dominant one. So detection in space is actually the most important one for the particle physics community, because it corresponds to the electric wave transition, right? But detecting it can be very challenging. Previously, people only considered a single detector, and there is in principle a method, the so-called null channel method, that we can use to detect it. So let's go to very details of a detector. So for space detector like IISER, Tiantian-2 detector proposed by China, by the way, we have to use the so-called time delay interferometry to cancel the dominant noise from the laser frequency fluctuations. And then we will have roughly 3 TDIs, the so-called TDI channels, and we use one channel to monitor noise and use the other two to measure the signal. This is called now channel method, but it can be very challenging actually to detect this kind of noise. This noise-like signal because the real detect might be very complicated. But still, people have used this technology to try to see the implications for phase transitions. For example, Gino and Marek and others and Himars, they have done a lot of this kind of started in recent years. And another possibility is that we can consider a network like the Lisa and Hetty network. And in this way, we can use the standard cross-correlation method. So this method might be ideal scenario for the detection of the phase transition gravitational wave in space. Of course, it depends on the coordination of the different collaborations. So far, based on this scenario and with a realistic contribution, realistic consideration of the sources, for example, the foreground and astral background, we can probably detect the stochastic background of the cosmological origin down to 10⁻13 if we speak about omega. In recent years, there are also positive evidence for the detection by the PTE partial timing array experiments, and people have also tried to study the implications on for the scenario where phase transition is the signal. For example, this is one by non-Grav together with all other new physics sources, and this is by EPT and India PTA. And we have also, with Tathagata and other collaborators, try to fit to the data with more precise prediction for the sound wave spectrum. So right now, for all the detection, there are problems because there are uncertainties, not just the systematic uncertainty on the experimental side, but also the uncertainties from a theory side. So this is taken from a paper from this paper, and this source of uncertainty comes from the final temperature field theory calculation, and this is from our paper about on the uncertainty coming from the calculation of the phase transition parameters, and this is from another recent paper of ours where there are some minor kind of uncertainty coming from some analytical formula we use, so this is by comparing the analytical formula and the numerical simulation that we have done. So there are two plots given by Peter Ethering and his collaborators and Marek and his collaborators showing the intuitively the uncertainty on calculation, for example, on the critical temperature and on the inference of the model parameters using for the uncertainty from the finite temperature for the effect from the effect potential calculation. You can see right now we have kind of large uncertainty for both kind of scenarios. So to face possible kind of discovery in future detection, we need to make more precise predictions for the entire chain of calculations. And if we look back at this picture, initially we saw a bunch of bubbles, but if we look closer at each bubble, you can see that there are fluid motions, as I just mentioned earlier. And there are different fluid motions and called detonation, deflagration, and the so-called hybrid mode, supersonic deflagration. There are different fluid motion, and if we add all these bubbles together, the entire picture can be very complicated. So I will now only talk a little bit more about the sound wave contribution. So far, the result that we have used comes mainly from the two approaches. One from large-scale numerical simulations. This was majorly done by the Helsinki group and others. And the other method is by using the analytical method. So we can try to construct the model of the flow motion and try to calculate the spectrum analytically and try to see if this result matches well with the spectrum found from the simulations. And the model is called the sun shell model proposed by Hindmarsh and his collaborators. And we also try to improve on this model, and several other groups have also tried to do so. And it is through this kind of numerical and analytic approaches that we can probably understand better about the spectrum. Of course, aside from this thing, there are also higher approach like the one proposed by Gino and Thomas Constantine and others. So if we look then at the spectrum, that's what obtained from simulation and analytical modeling, they're basically so it basically looks like this. So the source in this case is actually TIG. So this might look complicated, but it's actually it's come from the perfect fluid kind of form. So the one that we usually use in cosmology. So the spectrum was obtained by the Helsinki group from numerical simulations, and this factor comes from the modeling and following the sun shell model. And as I said earlier, this also described the effect of the sound waves, the gravitational production from the sound waves in an increasingly diluted kind of cosmological context. So as the plasma is being diluted, you will see that the gravitational wave production will become slower. Reflecting in this figure, you will see that the slope will become smaller and smaller. Eventually, when you reach this point, for example, you will have the full production of gravitational wave, where epsilon approaches 1. So recently we have generalized this Wolfram factor. So let me explain a little bit more about how it was obtained. So in calculating the stochastic background of gravitational wave, we first calculated the gravitational wave amplitude HIGA, and then we calculate the correlator, which is proportional to the energy density spectrum we obtain. We eventually want. So this P, this capital P actually is just the omega GW. So if we calculate, so this HIGA is a function, an integral over time. This is another way of writing time, and this pi IGA is the part in team IGA that can generate gravitational waves. So when we calculate the correlator, we will have two time integrals, right? We have one here, and when we calculate the correlator, we have two. And in its context, you will notice that because the feature of this process, the following features, so the source is Gaussian and to a large extent and stationary also, and the autocorrelation time is much smaller than other time scales. So the autocorrelation time is one quantity that describes a stationary source. Stationary means that the correlator of this source is proportional to the time difference. And if the time difference is much smaller than other time scales, you will notice that you can do the following trick. Firstly, we do a change of variables from y1 and y2 to y plus and y minus. Y minus being the autocorrelation time. Then, if y minus is much smaller than other time scales in the problem, then you can drop the y minus in this part, which integrates basically the time. And then you will find that there will be an epsilon factor, which so this will give you a factorized form for the gravitational wave spectrum. Of course, this is obtained with approximations, but the approximation is very good, at least near the peak frequency, and for region near this, I will talk more about the kind of deviation from this factor. So far this factor is frequency independent, and this is this is the results of these behaviors that the sound wave satisfies in this context. So that's the reason. That's the reason why we have a overall largely frequency independent Wilson factor, which describes the growth of the gravitational production from the phase transition from sound waves. And the reason is that we have tried to generalize the Wilson factor to a general context. So let me explain a bit more about this. So previously, in our previous paper with Graham White, Koushik, and Daniel Viggi, we give two results. One is for the sound wave in radiation domination, and the other sound wave in matter domination. So the matter domination and radiation domination refer to just the expansion rate of the universe. The sound waves they appear in actually a plasma medial relativist particles. Basically, it's radiation, but we can have a different expansion rate. For example, matter domination if there's another set of purely non-relativist matter, right? So if we consider further the problem of a generic background expansion rate, but still have a sound waves in the radiation sector, then for the general equation state given by this euro kind of symbol, and with this expansion rate, we can obtain a very compact result similarly as previously obtained. So where or why here denotes the skew factor ratio. The skew factor is basically another way of measuring time, right? So it's a skew factor ratio. The one sits on the numerator is the one that's the current time, and the one on denominator is the one the time is given by as the time when the sound waves become active. So this is the measure of basically time. And for generic equation status, and even though the calculation of the whole process is very complicated, we can, through this approximation, obtain a very compact results. And for radiation and matter, for radiation domination and matter domination, you will notice you can easily reduce this result into the same result that we have obtained earlier. So probably this scenario this expression can be useful for people who consider more exotic phase transitions. Recently, there's another development in this field. So it's given by Xiaojian and others in China. And they said that in their scenario, before the further propagation of the sound wave, there's another period when the sound is driven by the scalar field. So there might be another contribution before the further propagation of the sound wave. So probably we should add the two together. But we need to scrutiny more about this. And of course, if this is important, we need to certainly include this in the experimental on the experimental side. So the other thing I want to say is about the behavior when the approximation that lead to the Wilson factor fields. So these are given by the works of Kaplan and the other group and Helsinki. They both studied the low frequency region and found that the growth of gravitational wave spectrum is different from the rate given by this Wilson factor. And there should be another factor that should be used, and you can go to these two papers for details. Aside from this growth of the overall amplitude, there are other things that they have found. So previously we have said that there's k cubic at very low frequencies, right? But actually we can have a linear growth of the spectrum k to the first power and k to 9th before reaching the peak. So all these scenarios probably should be taken seriously if we were really try to detect this using real experimental data. So lastly, I want to see a little bit about some other works of mine regarding the spectrum from sound waves. It's a dissipative effect that people have largely neglected in the consideration of this source. So what is this? So basically, the kind of viscosity that you have when you compare honey with water, right? So viscosity differs a lot. It's exactly this kind of viscosity that probably can lead to a difference in the spectrum calculation. So mainly this effect can be understood very simply using from this only from this slide. So if we start from the Einstein equation for that describes gravitational waves.
Hello? Yeah, we have 10 minutes left.
Oh, thank you. Thanks for the reminder. And we can then do an order of magnitude estimation of the gravitational amplitude. And you can see that this amplitude is determined by the mass of this system and the distance of this source from us, and the overall, the bulk velocity of the matter in this system. So if you plug into the mass of for example, binary black holes and distance and the velocity, you will roughly get the same kind of value for the magnitude. If we talk about the paper, the first detection paper of LIGO. So this gives you an order of magnitude estimation for the gravitational amplitude, and you can see there's a velocity. So then this is not the velocity of the single particle in the system, but rather the bulk velocity of the fluid or the matter in the system. And the dissipation will reduce the velocity. So this is the Navier-Stokes equation, and with dissipation, for example, shear viscosity, bulk viscosity, you can see that it will reduce actually the velocity. If you integrate, if you use this equation and calculate the kinetic energy mv squared, then you will find that the kinetic energy will be reduced. So consideration of the dissipation will reduce the gravitational wave production. That's the single kind of conclusion. Of course, going to more details, we can use the sum shell model to see more details about how this reduction happens. So this framework actually has been given by Steven Weinberg back in the 1970s, and we consider the viscosity and the other kind of damping effects like thermal conduction. We then can find that the velocity field will be damped in this exponential way. There is a rate here. This is proportional to Q squared. So if we look at this expression, you will notice that you will then conclude that the velocity will be more suppressed for large wave number or small scales. So this is a phenomenon. Actually, you can obtain even without this complicated relativistic formula given by Weinberg, but you can find that in any kind of fluid mechanics book. So this is the conclusion. The velocity field will be more depth for higher frequencies or higher wave numbers or small scales. So we can take this into account by in calculation of the spectrum from sound waves by using the sound shell model. So the velocity perturbation from each bubble will be added linearly in the sound shell model to obtain the total velocity field. And for each perturbation of the fluid, the sound or the velocity field, there will be a damping effect. And if we add all these together, we can get the total velocity field. Then we can, because it's a random kind of field of space, what we actually need to calculate is the power spectrum for the velocity field. So, and here this is result for the velocity power spectrum, and the blue one is without dissipation, and the dashed ones are with dissipation effects with different kind of magnitude for the dissipation. You can see the spectrum will be firstly damped for higher frequencies, and of course, if this effect is very strong, then it can even shift the peak frequency to lower values. So with this velocity power spectrum, we can then go ahead to calculate the gravitational power spectrum. You can have a similar kind of phenomena. So we have a damping of frequency to the spectrum starting at higher frequencies. So this phenomenon is actually very similar to the silk damping in the CMB anisotropy that we observe. So without this silk damping, what we calculated is the blue dashed one, and with the silk damping, what we observe is the red one. So the cyclic damping comes from the increasing mean free path of the photons during the recombination era as less ion particles appear in the environment. And the similar things can happen if we have very weak interaction or freezing out of some particles, and probably this is some direction we can explore in the future. And the dissipation will also affect the lifetime of the sound waves, and because it reduces the gravitational waves, right? So we can define some effective lifetime so that beyond that there will be very little production of gravitational waves. So if we take this into account, then we can see three factors of determining the life of the sound wave, which so this is the parameter that enters the ozone factor that determines the overall amplitude of the spectrum. So firstly, the expansion of the universe will provide some damping effect, right? Then the dissipation, then the other one is usually quite often in literature is the onset of turbulence. We just cut off the sound wave production, but starts the turbulence part of the gravitational waves. So all these will determine eventually the final precise lifetime of the sound waves. In related cases, probably intertwining of these effects will make the spectrum quite more dependent. It's quite messy, but probably this model dependent information can carry more information about each model, and they can break the parameter degeneracy in this field. So this is all I have to talk about this topic, and it's now an important target for all the experiments. And right now, the precision study is become of high priority, and there has been some progresses for the sound waves part, and there are also some effects probably we need to take into consideration in the future. So that's all for my talk. Thank you all.
Okay, so thank you for the nice talk. We have some time for question and answer. Anybody?
Hi, this is Ryusuke. Nice to see you. Nice to see you again. So, do you have any updates for Taiji and the Tenji? If you have any.
Hi. Sorry, I always find it difficult to pronounce your first name. So I think it's hard to say. So far, there are no concrete news. Probably there will be some. I cannot see more about this thing, unfortunately. It's a very good question.
Sorry.
Very difficult to say.
I'm sorry.
Yeah.
The question? Yes, please.
Sorry, another question. So in the slide 2023, maybe the spectral looked flat. Yeah, the spectral looks flat. And could you explain why this looks flat?
So what's the thing that you ask? So
is this normalized by k times some constant? Okay.
Yeah, yes, you're right. Yeah, k. So it's k to k squared, right?
I see. Thank you.
Yeah, this is taken from I think Kara's paper. I think so.
Any other question? I have one small curiosity. So when you were showing the effect of matter domination, was it a period of early matter domination, or was it the late time matter domination?
So you mean this part, right?
Yeah. So is it for a period of early matter domination?
So it actually doesn't matter. So it just we have a sector where there are some waves, right? And we have another probably can have more energy, can then determine more of the expansion rate.
I see. So you can use.
Yeah. Right.
So then probably you can use the same, same formula for a scenario where you have a period of early matter domination, right?
Yes, right, yes.
So in some cases where you have period of early matter domination, you usually have like a scalar field which dominates the universe in early time, and then it decays in injecting some amount of entropy, right? So
Mm.
so does this factor also consider the fact that there might be some entropy injection coming after the period of early matter domination?
No, I think that's a question. In more exotic kind of or realistic scenarios, we do have this transfer or generation of entropy. This factor does not. It's only considered into the dilution of sound in expanding universe and determined given by some expansion rate, right? In a scenario that you consider, let's see, there will be entropy injected, probably can slow down the universe expansion or increase a little bit more about the temperature. It's not included here. If the feature transition happened at the same time, right?
I see. Thank you. I think
Probably
there is
we have to consider this case by case. This is just some some kind of context, some fixed context.
So, Hu-aike, just one last question. So, when you are talking about these dissipative forces, you mentioned new physics, right?
So just intuitively, I think there might be some connection. I think Gino probably has something similar. I'm not sure they are connected. So yes, so the circle connection comes from the increasing so from the photon, right? They have the increasing mean free path, so you can travel more further from the hot region to the cold region and to carry energy and around, right, to make this universe more homogeneous. So in this case, I think probably similar thing like the freeze out some particles or some kind of very weak interaction probably can be can give some this kind of effect. So far, it's more independent, but I think if we consider so in the early universe, usually the viscosity I think is very small. But if we consider new physics, like what you said, I think there might be a way to make this strong. That's what I have intuited, but so far I haven't considered the more details about the particle physics origin. But there is postdoc here who is now working on this.
Thank you.
Yeah, if you know better about how this happened, please let me know. We can work together on this.
So let's thank the speaker once again.
Thank you all.